Our next item is we're going to talk about what's called the 5-number summary and box plots. And the 5-number summary is going to involve what are called quartiles. And quartiles are just how you split up your data so that each quartile contains a quarter of the data. If you were to talk about your quartiles, Q2 is the median. Okay, so we'll talk about exactly how to do this, but Q2 is going to be the median, and then the median splits your data into a top half and a bottom half. And then in each half, you can split it again, and that's going to be your first and third quartiles. I'm trying to think of which one I just showed you because you're backwards to be. So this would be first. So here's your median, and then your first quartile and your third quartile, because we're facing opposite directions here. So here's a picture of what I'm talking about. So Q2 is just the median of your data. Q1 and Q3 are going to be the medians of your lower half and bottom half of your data, respectfully. Okay, so those are quartiles. And that's actually already 3 of the 5 numbers that are used in the 5-number summary. Okay, so those are quartiles. There's really not too much more to talk about that. There's what's called the interquartile range, or IQR, which is defined as Q3 minus Q1. And roughly half of the data should be between Q1 and Q3, because the quartiles have 25% of the data in each quartile. So if you were to think about Q3 minus Q1, so somewhere in there, if you were to think about that, that should have about 50% of the data, no matter what distribution we have, right? If we go from Q1 to Q3 in any of these, we should have about 50% of the data there. So that interquartile range is defined as Q3 minus Q1. And then the 5-number summary, very straightforwardly, is going to be your 3 quartiles, Q1, Q2, Q3, plus your minimum and your maximum. Okay, and that's again called the 5-number summary of a data set. And those 5 numbers can tell you quite a bit about what your data is actually looking like, how it behaves. Now, we're going to care a little bit about lower and upper limits for our data set, and these are defined as follows. So the lower limit of your data set is going to be Q1 minus 3 halves times IQR, and your upper limit will be Q3 plus 3 halves times IQR. 3 halves times the IQR is used, if we think about what the IQR is it's going to be about half. And so 3 times that is going to give us kind of our lower limit and our upper limit of our data. And then potential outliers are going to be the values that lie beyond the lower and upper limit. So those are going to be useful to have identified there. And again, those are just potential outliers. It's kind of a subjective decision about whether you want to call any particular data point an outlier or not. But we'll talk about that as we go. All right. The last thing that we're going to do in this section is talk about how to construct a box plot. And a box plot, or sometimes a hair and whisker plot, is going to be a plot that's used to kind of give us a very succinct summary of the data using these ideas that we've talked about in this section. So using the quartiles and the min and the max and so on. And so what we're going to do to draw a box plot is the following. So here we have, don't worry about what the actual numbers represent, but here we have 20 numbers. And what we want to do is we want to draw a box plot that gives us a kind of a quick glance summary of what's happening here. Box plots are very useful when you have 2 different sets of data and you want to compare them. Box plots are really good at comparing different data. But what the box plot's going to do is we're going to write down the Q1, Q2, and Q3. We're going to write these down with vertical bars here. This is the whisker part of the hair, or this is the whatever. So these are the vertical lines that we're going to have for our 3 quartiles. And then we're going to write down the adjacent values. That can be the min and the max, but not including the potential outliers. So first you're going to identify the potential outliers. And then after that, you'll write down the min and the max without those potential outliers. And then you can connect them. You got your hair and whisker plot. Usually outliers are denoted with an asterisk and an asterisk. And that's it. That's a box plot. Box plots are not used frequently, but they are used sometimes when you're comparing two different data sets. So sometimes box plots are used when you have kind of a statistical survey of how useful is one medicine versus a placebo, or how useful is maybe you're tying two medicines versus each other, and you want to compare what do they do? What are the mean recovery times for your different medicines? And your box plot will kind of give you an overview of which one is better. So this is how the box plots are made. Yeah, so here's an example. If you have two different data sets, your box plot can really just give you a glance of what's happening in one data set versus the other. Okay. One thing that I wanted to mention, and I actually need to go back and talk about just for a second, is Q1 and Q3. And you have to make some decisions when you have your quartiles. And this is something that's going to come up when we do these in practice. But we have to make some decisions. So in particular, what I mean is, and there's lots of ways that you can kind of choose to deal with this. But if you were to have, let's say you were to have a data set, let's do a quick example here. I want to add this in. So let's say you were to have some data set, and let's just make the numbers nice and easy for us. 1, 4, 1, 4, 6, 7, 8. Let's actually add a few more values in just to make it slightly more interesting, say 10 and 10. So here's our data set. We have 7 numbers, and our median, which is Q2, is 7. The way that the book is going to go about finding Q1 and Q3 is that if you have an even number of data points, you're not going to include the median in your lower and upper half. But in our case, we have an odd number of data points, and so we are going to include the median in the lower and upper half. So what I mean by that is, if 7 is the median, this is going to split the data into 2 halves. We're going to have 1, 4, 6, and 7. And this is going to be what I call the bottom half, or the small half. There's also the top half, which is 7, 8, 10, and 10. And then Q1 and Q3 are going to be the median of these two numbers, of these two groups of data here. So for Q1, your median is going to be, here we have an even number of data points, so we're going to take the mean of the two middle numbers, so we'll get 4 plus 6 over 2. So here we have 5. And for Q3, we're going to again take the mean of the two middle numbers, that's 8 and 10, and that'll be 9. So it turns out that for this particular data set, Q1 is 5. Okay, so Q1 is 5, Q2 is 7, and Q3 is 9. And that's how that's going to work. Now, on the other hand, let's say we have an even number of data points. So let's say we have 1, 4, 9, 10, 11, 13, and 20. Okay, so here's a new data set, and I want to compute Q1, Q2, and Q3. Q2 is just the median, and that's easy because we have, what? What am I doing here? I have, I want to have an even number of data points, sorry. So let's, yeah, that's fine. Let's add one more value, say 21. So here I have 1, 2, 3, 4, 5, 6, 7, 8 data points. The median of this data set is going to be the halfway point between 10 and 11. So it's going to be 10 plus 11 over 2. So that's 10.5. And then this is going to split the data into 2 pieces. And here we can actually think of it as splitting the data into 2 halves. So we have 1, 4, 9, and 10, 11, 13, 20, and 21. And so now for 1, 4, 9, and 10, Q1 is going to be 4 plus 9 over 2. So it's going to be 13 halves, or 6.5. And for 11, for 11, 13, 20, and 21, the median there is going to be 13 plus 20 over 2. So that's going to be 33 halves. 33 halves, so 16.5. Okay, so we have to make a decision about, do we include the median in the lower and upper half of our data? Do we not include it? Is there another choice that we can make? And there's lots of choices, actually. In fact, in the statistical software R that we're going to use, there's actually 9 different ways that you can split up this data to compute the quartiles. So we'll talk about, our book uses what R calls method 7. So we'll talk about exactly what that means when we do R. But that's the 5-number summary and box plots, just very quickly. And then finally, in our last section, we had been talking about sample standard deviations and sample means, but we can also talk about population standard deviations and population means. And everything is basically the same. For a sample, so our sample size, we use little n, that's the number of data points we have in our sample. For a population size, we're going to use capital N. In math, generally lowercase and uppercase numbers are, lowercase and uppercase letters denote different values. So they're going to be different numbers. So sample size will be little n, population size will be capital N. And we have different notations for these things as well. For the sample mean, we had X bar for the sample mean. For the population mean, we're going to use mu. Now this is defined basically the same as what it was before. You add up all the values, you divide by however many data points you have, you divide by the population size, and that's it, that's the mean. So there's not really too much there. The standard deviation, however, is going to be different. So the standard deviation for samples was S. For populations, it'll be sigma. And the difference in what's going to happen here is, notice the denominator. For samples, we had little n minus 1 in our denominator. Okay, so we still took X, we took our data points, subtracted the mean, squared them, added them up. But for populations, we divide by the size of the population. For samples, we divided by little n minus 1. So there is a difference here about whether we'll talk about a population standard deviation or a sample standard deviation. In general, the rule is that if we just say standard deviation, we mean sample standard deviation. We will always say population standard deviation if we mean that. Okay, so the default is that we're always talking about sample standard deviation unless we say otherwise. Just like there was a computing formula before, there's a computing formula here. So there's our formula for it. By the way, all the formulas will be available for you on a handout that you can use for each exam. And that's really the only difference in sample versus population standard deviations and means. I do have to say, again, we do use different letters here. And the last thing that's worth talking about here is a parameter versus a statistic. So a parameter is going to be some sort of descriptive measure, meaning a mean, median, mode, or standard deviation, range, whatever. And a parameter means that we're talking about a population. A statistic means that we're talking about a sample. So when we do statistics, we're kind of inherently talking about samples. Okay, so that's the difference between a parameter and a statistic. We will talk about, I'm actually going to put off standardized variables until chapter 5, so we'll talk about that later. But that's a parameter versus a statistic. Okay, so parameter describes a population, a statistic describes a sample.